some reason so you can all hear me properly, right?
Yes.
Just 1 minute. ठीक है, अब सही है. Acha, so let's quickly start with the first question. The first question is about. As the first question is about. You're given the mass spectrum of silicon, so it's got 3 isotopes. So you can quickly try and figure out what the mass of those 3 isotope is. So calculate the AR. What's the formula? The relative atomic mass of this thing would be. Okay, it's going to be the percentage multiplied by what's the percentage of 28. And remember the relative intensity. It's out of 1. So you're looking for the fractional percentage. So it's 0.922, which is 92.2%. So it's 0.922 multiplied by the AR, which is 28. Then you're going to multiply 0.047. And that's going to be multiplied by the AR, which is 29. And the other one is, the isotopic mass is 29. And the last one is 0.031. And that's going to be multiplied by 30. So Ethan, Mohammed, Adam, anyone quickly tell me what the answer is? What are you getting for this?
We have 28.109.
So you're getting 28.10109. And he said that you have to write your answers up to 2 decimal places. So it's going to be 28.11. Okay, I think that's going to be what you're going to get up till 2 significant figures. 2 decimal places. Now, silicon forms a low boiling point chloride with water. Remember, chlorides, when they react with water, that's period 3 AS. So if you've got silicon chloride, it's going to react with water and there's going to be vigorous hydrolysis. It's going to form silicon oxide plus there's going to be HCl gas, fumes of HCl gas, white fumes that are going to be produced in the reaction. Remember, all chlorides, they kind of hydrolyze except for the first one, which is NaCl. NaCl only dissolves. MgCl2 mostly dissolves, but some of it is hydrolyzed. After Al in period 3 and silicon and phosphorus, they all have hydrolysis. And then you have to draw the 3-dimensional silicon of SiCl for this one. So silicon is bonded to 4 atoms. It's got no lone pairs. So if it's got no lone pairs, the shape of a silicon atom or around the silicon atom is going to be tetrahedral. So remember your shapes of molecules. And these things just draw and also write the bond angle. So that's 109.5 degrees. So that's the answer to this part. The next one, moving to the next page, You've got silicon reacts with oxygen to form a high melting point oxide. So with that is SiO2, that's a giant covalent structure. So it's this structure. What happens is that every silicon atom is bonded to, it's bonded to 4 oxygen atoms in a tetrahedral arrangement. And then those oxygen atoms are further bonded to silicon. And then those silicon atoms are further bonded to 4 oxygen atoms. And it just continues. It's a giant covalent structure. So it suggests in terms of the structure why it has a high melting point, whereas the chloride has a low boiling point. So the chloride of, I mean, the SiO2 has a high melting point because it's a giant covalent structure. That's the reason. With many strong covalent bonds. Now, at the same time, so with many strong covalent bonds, why is SiCl4 having a low boiling point? You need to explain that as well, because SiCl4, as we discussed, was a tetrahedral molecule. That's it. I mean, this was it. It wasn't a giant structure. It was just a simple molecule. So if there's another SiCl4, they're not going to be bonded together. So you don't have to break any bonds. The only thing that's between them are weak intermolecular forces or weak van der Waals forces. So they don't have much in common. They're not going to attract each other. So for SiCl4, you're going to write that SiCl4 is simple molecular with weak van der Waals forces. Okay, is this clear? Mohammed, is this clear?
Yes.
So then element A is in the same period as silicon. Element A reacts. So what is in the same period? So you've got A. In silicon's period, you've got Na and you've got Mg, you've got Al, you've got silicon, that's also, and you've got phosphorus, sulfur, and chlorine and argon. So these are the elements. Now he's saying it reacts with dilute nitric acid to form a nitrate. So it must be a metal, probably sodium nitrate or magnesium nitrate, or maybe aluminum nitrate. And the nitrate decomposes on heating to form an oxide. So it's also getting decomposed as well. So write an equation for the decomposition of the nitrate, and the oxide of element A has a high melting point, suggests the structure and bonding present. Now for decomposition, the only ones that you should be aware of are group 2 nitrates. So it's going to be a group 2 nitrate. It's going to be magnesium nitrate. Okay, that's the one that's in your syllabus. And it would decompose to form MgO plus NO2 plus oxygen gas. That's how all nitrates decompose, and it's got a high melting point. So what's the structure of the oxide of element A? What is MgO? MgO has a pretty high melting point, and the reason for that is that it's a giant ionic lattice with really strong ionic bonds. So it's just a 1 mark question. The ionic lattice is going to look like this. This is going to be Mg2 plus, this is going to be O2 minus, which would be attracted to Mg2 plus, and then it would be attracted to O2 minus, and it just continuously repeats. They're all attracted to each other, and they're very strongly attracted to each other because Mg is a small ion, and O2 minus 1 is also a small ion, got great charge density. So they're going to attract each other very, very strongly. Okay, is this also clear?
Yes.
So then you have to figure out the signs of electron affinity of all these enthalpy change values. Remember about electron affinity that it could be positive or negative. Why? Because when it comes to gaining electrons, the first electron is always exothermic because It doesn't need energy because oxygen is a neutral atom, and if it's a neutral atom and it's highly electronegative as well, so it's going to try and gain that electron on its own. Okay, the first one is always exo. The next one becomes difficult. You've got oxygen 1 minus and it's gaseous. It tries to gain another electron and it becomes oxygen 2 minus. Now, the reason why it's more difficult to gain the second electron is that the ion is already negatively charged. Negatively charged ions, they repel electrons. So they're not going to be very strongly attracted to those electrons. So that's the reason for this. That after the first one, they all become endothermic. So the first one is positive and the rest are all endothermic, and it becomes increasingly endothermic. Like oxygen 2 minus, that would be even harder for it to gain electrons because it would essentially be repelling electrons. Atomization is always endothermic because you have to break bonds to form atoms, and breaking bond is endothermic. Ionization energy is also always endothermic because you have to remove electrons, and it always requires energy to pull an electron and take it away from the nucleus. And lattice energy is always exothermic. It's always exothermic. Why? Because you're forming bonds. Lattice energy it's the energy that is released when a lattice is formed. An ionic lattice is formed, like this one. Na+1 and Cl-1, they get together to form an NaCl. Gaseous ions, they get together to form a solid ionic lattice. So whenever an ionic lattice is formed, bonds are formed. Now he's given us the Born-Haber cycle. Just 1 second. What's the question? Other ionization energy is, what is ionization energy? It's you trying to remove electrons, right? For example, here's an atom of sodium. Okay, let me just come up with some images. So let's say this is an atom of sodium. Okay, the one that's over here. So ionization energy is that it's you trying to remove an electron. So you see this electron over here, you try to remove it. That would require energy because the nucleus will be attracting this electron very strongly. So it would be very hard to remove electrons. A lot of energy would be required because this nucleus over here is trying to pull that electron. So it's going to be endothermic. Is this clear? So it's always going to be endothermic. As the next is our Born-Haber cycle. Now your Born-Haber cycle is, they've already drawn the Born-Haber cycle. He's saying, so I'll just quickly go through the Born-Haber cycle, what it contains. It starts off, you can start off at enthalpy of formation. Enthalpy of formation is delta HF. That's your enthalpy of formation. Elements, they join up to form MgCl2 solid. So that's enthalpy of formation, that the elements are combining to form 1 mole of ionic lattice. That's enthalpy of formation. And the other route is, that's one path. You go from this point to this point. So that's one of your paths. You pick these elements, you form the ionic lattice. The other path is according to Hess law, one path and the other path are equal. The other path is you go all the way around and form this. What do you have to do? You would have to atomize Mgs because it's metallic. All the Mgs are bonded together. So you would have to break those bonds. So enthalpy 1 would be atomization. Okay, let's start writing this. This one would be atomization of Mg specifically. So that's going to be atomization. Then you've got over here it's atomization of Cl, or you're just breaking the bond of Cl. So you're atomizing Cl. So this would be equal to the bond energy of Cl and Cl. You're breaking the bonds, you're turning it into atoms. And then you're going to ionize it. Mg is being ionized, and they're going to be 2 ionization energies because Mg has to turn into 2+. So this step over here is the first plus the second ionization energy. Because Mg went from Mg atom to Mg plus 1, then Mg2 plus. So it's first plus second ionization energy, and then there's electron affinity. It's Cl gaining the 2 electrons. So it's electron affinity of Cl. So that's the opposite of, so that one is electron affinity of Cl multiplied by 2, because you've got 2 Cls. And the last step is, once you've got these gaseous ions, the ions are going to get together to form the ionic lattice. So the last step, this enthalpy 6, is going to be your lattice energy. Okay, is this clear, everyone? All good?
Yeah.
I said then, so that's your lattice energy. So why is delta H4 greater than delta H3? So you've got delta H3, you've got delta H4. So why is, so I'm going to just copy a magnesium atom. Okay, so let's find out in Mg atom, because he's comparing the first plus second ionization energy. So I'm just going to copy this. Let's just copy this atom and copy it here. So I've gotten my atom, and just hold on 1 second. Let me. I've copied my atom over here, and just hold on 1 second. Let me put this to charge. So where's the atom? Here's an atom. We're trying to remove 2 electrons from this atom. So I'm going to try and remove the first electron first. Removing the first electron is easier compared to the, I mean, that's the first one. So we're trying to remove the first one. So that's our first ionization energy. And then we're going to try and remove the second one. That's our second ionization energy. So what goes wrong? I mean, you've got the same distance. Everything is the same. I mean, I'm not going to write same distance. Actually, what I'm going to do is I'm going to call it the same shell. Just 1 second. So I'm going to call it the same shell. Electrons are being removed from the same shell. So what are the factors that you've got the same shielding? Now, what are the factors that actually affect ionization energies? You've got proton numbers. That's not a factor because it's the same atom. The distance kind of looks the same. It kind of looks the same. You've got the same shells. So, I mean, removing the electrons would probably be this. I mean, it would require almost the same energy. But the thing is, once you remove the first electron, I mean, removing the first electron, the only thing that changes now is that once you remove the first electron, it becomes Mg1 plus. So when you're trying to remove the second electron, you now have a net positive charge on the whole thing. So that's the only variation that's happening. Now, because of that single variation, because of everything else kind of remains the same. So because of that single variation, removing the second electron becomes kind of difficult because you're now trying to pull an electron from an ion that is already positively charged. So if it's already positively charged, it's going to attract the electrons a bit more strongly. So you're going to state over here that in delta H4, electrons are removed from a net positive ion, which leads to greater attraction for electrons because now it's positively charged. So it's going to be much harder to remove. It would be much harder to remove electrons. So there's going to be greater attraction for electrons. And the ion size would also decrease because of the greater attraction. Although the shell is the same, it would be a slightly smaller ion as well. Okay, because once you remove the first electron, the atom or the whole thing becomes positively charged. So the attraction of the electrons is slightly stronger. So this electron would actually be slightly closer to the atom in this particular case. And you can also talk about the net effective charge, that it's an overall positive ion now. So it's harder to remove electrons because the net effective nuclear charge is higher. Is this point clear? Mohammed, is this clear? Adam, is this clear? So I'm just going to sort of check the phrasing of the answer. What specific word? Because they keep changing for this one. So just very quickly, I think this is the marking scheme for this one. Nope, not this.
Sir,
Yes.
can we say it's removed from a single pair electron instead of a double because spin pair motion?
No, not that. I mean, that's it. They were just saying that the second electron is removed from a more positively charged ion. Okay, now about the thing that you stated. The thing is that whenever you're removing electrons, the subshells and the orbitals don't really matter except for the cases where you're removing electrons from group 3 after group 2 or from group 6. The orbitals and subshells and the spin pair repulsion and the higher energy or lower energy orbitals, they're not that big a factor. Is that point clear?
Yes.
So what names are given to enthalpy changes delta H 6 and 7? We already did that. 6 was lattice energy because gaseous ions were turning into solid ionic lattice, and 7 was enthalpy change of formation because elements were turning into a solid ionic lattice. Achha, next is, what's the next question? These things suggest the trend in the electron affinity of the elements in group 17. Explain your answer. So the trend is probably who really likes to gain electrons? It's probably the top ones, the smaller ones. Electronegativity decreases. I mean, smaller atoms are less shielded. Or less shielded. And if they are less shielded, there's going to be greater attraction for electrons. It's going to be more exothermic. They will pull the electrons with a lot stronger force. Bigger atoms, they already have too many electrons and they're very shielded. The nucleus is very shielded. So there's going to be greater attraction for electrons. And so hence more exothermic. So even this one we can quickly check what's the, so electron affinity becomes less exothermic. That's true. So it depends mainly on the electron nucleus distance, which he did talk about distance over here. Not shielding, which should be acceptable because shielding and distance both are kind of the same. So anyways, over here, they actually, I mean, we should have actually gone in full. We should have mentioned all the factors so that even the factor that's not listed, I mean, shielded has to be true. It's not possible that shielding is not increasing. 1 second. So up the group, there's going to be smaller distance. Okay, so down the group, the smaller atoms are going to be more exothermic. So we should have listed all the ones, even the ones that are not mentioned. That would have been correct. So I'm just going to, can you quickly tell me what delta G is? What's the formula for delta G? It gives free energy. Anyone, Mohammed, any idea?
Delta H minus T delta S.
Okay, so that's delta G is equal to delta H minus T delta S. And remember, it either or everything has to be in kilojoules or everything has to be in joules. Now for this, you need delta H first. Delta H is already given. That's listed over here. That's already given. So what else do you need? You need delta G. You need delta S now. I mean, the temperature is given. That should be in Kelvin. So that would be 298 Kelvins. Delta S is not given. Delta S can be calculated using the formula that it's the entropy of the products minus the entropy of the reactants. So entropy of the products minus entropy of the reactant. So the product entropy is MgO, that's 26.9. And the reactant entropies are Mg, that's 32.7. Plus half oxygen molecule, that's 102.5, then half of that. So can you plug in all the values and tell me what the answer is? The enthalpy change is given as minus 602. I'm going to convert that into joules. Minus T, that's 298. And what's delta S that we just calculated over there? What are we getting for delta S? Or we can simply just
Negative 108.3.
So you're getting negative 108.8.3. I converted everything to joules. And you can then find this value. So we can just quickly refer to the market scheme. It is coming out to be negative 108.3, and they converted everything to kilojoules because I think we converted everything to joules. So they're getting minus 570 for this. And I think that, as anyways, the units were up to you, so you could have chosen the other one. So that's this one. Let's move to electrochemistry now. He's saying there's an Fe3 plus Fe2 plus electrode, and he's trying to measure the standard electrode potentials. To measure the standard electrode potential, you need a standard hydrogen electrode. So which one is the standard hydrogen electrode? I mean, out of the two, which one do you think is the standard hydrogen electrode?
Left. The one to the left.
Take the one to the left. So that means A must be 1 second. So that means A must be H2 gas. And your B, what is B?
Platinum.
Okay, that's going to be your platinum electrode, or which would also act as a catalyst. And what's C? Like hydrogen is going to be in equilibrium with what?
Water.
No, H+1 ions, aqueous. And the concentration is going to be 1 mole per dm cube. Like you can be very specific. Just to be on the safe side, it's going to be H+1 mole. So, and the reaction that would be happening over here, that would be 2H+1 plus 2 electrons in equilibrium with H2 gas. So that is what would be going on. And what is D?
Salt bridge.
Okay, that's your salt bridge. To complete the circuit or to balance out the charges in the solutions. And there's Fe3 plus Fe2 plus. So what is E? mean, that's the other electrode, Fe3 plus Fe2 plus electrode. So, I mean, what would E be? Like if both of them are,
iron electrode.
if you have got aqueous signs, then E is also a platinum electrode. So that's also a platinum electrode. And F is going to be a mixture of Fe3 plus and Fe2 plus ions. And both of them are going to be 1 mole per dm cube. Here, both of them are going to be 1 mole per dm cube. So we can just double check this one. So it's 1 mole per dm cube. So they were very specific. You had to write the pressure as well. They were very specific. So just to be on the safe side, write the standard conditions. Remember, he was talking about standard. The reason he used the word standard was just to confirm. I mean, did he use the word standard? He did use the word standard here. So you had to be very specific with the conditions. You had to use the standard condition, mention that this is 1 mole per dm cube. This is, we didn't mention this one. H2 gas must have been at 1 atmosphere. It must have been at 1 atmosphere pressure. As anyways, moving on. Done with this. Label the diagram. Which one is the positive electrode? So you just open the data booklet. The Fe3 plus, the reaction that's going on over here is this one. It's going to be Fe3 plus gaining 1 electron in equilibrium with Fe2 plus. And the potential on this electrode is E naught is 0.77 volts. And on the other electrode, the potential is 0.0 volts. Right? So which one is the positive electrode? Which one is the negative electrode? Left or right? Positive. Which one is it?
Right one.
The right one. The higher potential is the positive one, and the lower potential is the negative one. So then you've got what? Then he says in another experiment, an Fe2 plus is connected to a copper 2 plus. Determine the standard cell potential connected by a wire, and the circuit is completed. Use the data booklet to. So you just have to go and open the data booklet and find these 2 electrodes, which I can just code those values. It's you've got an Fe3 plus electrode, Fe2 plus electrode. And the value is 0.77 volts. Can you open and tell me what the other electrode value is? The copper 2 plus copper electrode. It's going to be this reaction. Copper 2 plus gaining 2 electrons in equilibrium with copper. So in equilibrium with copper. So is it 0.34 volts or not? What are we getting for this?
Yeah, 0.34.
So what's the rule? The higher potential is the one that gains electrons. So this one is the higher one. It's the one that's going to gain electrons, and the other one is the lower one. That's the one that's going to lose electrons. The first one needs to be multiplied by 2 so that the number of electrons gained and lost are equal. So the first one needs to be multiplied by 2. So he's saying determine the standard cell potential. You can just subtract the 2 values. Higher potential minus lower potential. So it's going to give you what? 0.43 volts?
Yes.
Like if you, so you're going to get 0.43 volts for that. And that's it. He was just looking for the potential. It's a one mark, not the equation. So that's about it for this one. Let's move to the next one. You've now got, you now have a nickel. Explain this if the concentration of nickel 2 ions is decreased. So let's focus on this electrode and tell me where would the equilibrium shift. So it's nickel 2 plus 2 electrons, and it's in equilibrium with nickel. And the potential at the moment is minus 0.25 volts. So the question is, what's going to happen if nickel 2 plus ions is decreased? So if this is lesser, where would the equilibrium shift?
Left.
Okay, so it's going to shift to the left. Okay, according to Le-Chatelier principle, if nickel 2 plus concentration decreases, then it's going to try and increase it. It's going to do the opposite. And when the equilibrium shifts to the left, it produces more electrons. So the potential becomes more negative. Okay, is that clear? That the electrode would start, it would start to make more electrons. And the electrode would be more negative in this case. So is this clear?
Yes.
So then you've got the other one, which is you just have to figure out I mean, you're given the Nernst equation now, which is this one, which is exactly this one. Nernst equation is for non-standard electrode potentials, the one which, I mean, it's for the ones where you don't have a knot at the top. So it's non-standard potential. So because the concentration is non-standard. So you're given this electrode. All you have to do is you just have to plug in the values. And the first thing is I'm going to write down the electrode equation, which is this one. I mean, you can, which is this one. And the E naught value is minus 0.41 volts. And oxide species is the left one. It's the one that's formed after oxidation. And reduced species is the one that's formed after reduction. So our oxidized species concentration is 0.6 mole per dm³, I think. And our reduced species concentration is given as 0.15 mole per dm³. And Z is the number of electrons. So the number of electrons is this one. That's your number of electrons. So you've gotten everything. All you have to do is it's E naught. I mean, the old potential is minus 0.41 volts, I think. Here it's already given. Plus 0.059 divided by Z, which is 1 log of oxidized species, which in this case is 0.6 divided by 0.15. So what do we get for this?
0.37, negative 0.37.
Negative
37.
Negative 0.37, right? And that makes sense. Why? Because the concentration of the product is decreasing more, so the equilibrium is probably going to shift to the right. It's going to shift to the right. The forward reaction would be more favored, and if it shifts to the right, the potential always increases, becomes more positive or less negative. So that kind of looks fine. Then the rate of reaction question, you've got, he's saying, show the order with respect to each reactant. So you can just have a look. You can either just figure out which experiments you're going to compare. So if you compare experiments 1 and 2, what's happening? It's doubling, right? And this remains constant. You want to keep one reactant constant and alter the concentration of the other reactant. So what happens to the rate? How many times is it increasing?
4.
See here, that looks like 4. So if it's 4, that means it's a nonlinear relationship. It's a quadratic relationship. So order with respect to this one is going to be 2. So is that clear?
Yes.
And in your explanation, you're going to write this. You're going to write that if you compare experiments 1 and 2, ClO2 concentration, concentration square brackets, is doubled. One second, it's doubled. And rate is quadrupled. So it's non-linear. So just 1 second. So it's a. I mean, you don't need to write a non-linear relationship. That's sorry. I said that is definitely not needed. I mean, you're going to just write order 2. That's it. I said, what about OH? Now, rub off everything. Start working out on OH. Which 2 experiments should I compare now? Now this one is an easy question. You just have to compare 2 and 3, right? And the ClO2 concentration is not changing at all. This is what's happening to it. It's doubling. You're doubling it. What happens to the rate? It also doubles, I think. And how do you figure out the factor? It's going to be this number divided by this number, right? Is that clear?
Yes.
So it's going to be a linear relationship. So the first one was order 2. This one is order 1. Is that clear? And our rate is this clear? All clear? Ethan, Mohammed, is this clear?
Yes.
So it's going to be ClO2 concentration, order 2, and it's going to be OHI in concentration. And that's going to be order 1. Okay, so that's this one. Then you have calculate the value of the rate constant K using the data from experiment 2. So you can do that. You can just start plugging in values from the rate value, the concentration value in these, and you can find the value of K. We can try and find the units. The units would be, what would be the units? I mean, the rate equation is equal to rate. I mean, this is equal to rate. So that's going to be our rate equation. So it's mole per dm cube per second. So that's x s minus 1. Mole per dm cube into mole per dm cube squared is equal to K. So that would mean that x to the power 3 goes to the other side, and this would become x to the power minus 2, I think. So it's going to be x to the power minus 2, s minus 1, which would give you what? Mole per dm cube to the power minus 2. So minus 2, and this would be 6, and this would be s minus 1. And next one is easy. Heterogeneous catalyst. The reactants and the catalyst are in the same phase. Different phase. Homogeneous catalyst, the reactants and the catalysts are in different phase. Is that clear?
Yes.
So quickly tell me what's happening here. Manufacture of ammonia in the Haber process. Heterogeneous or homogeneous?
Hetero.
Okay, that's heterogeneous because iron is a solid and nitrogen and hydrogen are gases. Removal of nitrogen oxides from car exhaust. What is that? Heterogeneous, homogeneous?
Hetero.
ठीक है. And but what's the catalyst in this case?
Palladium.
Okay, that's a solid. You use a catalytic converter. Oxidation of sulfur dioxide in the atmosphere. Which one?
Homogeneous. No,
Do you
it's
get that?
also, yeah,
Homogeneous, right? Which one is the catalyst in this case?
yeah, for oxide.
Nitrogen oxide, right? NO2.
All right, nice.
So then you've got this reaction. You have to balance this equation. It's a redox equation. So when you have a redox equation, what you do is you balance the number of electrons gained and the number of electrons lost. They need to be made equal. So for that, when you're trying to balance, so when you try and balance this equation, what's going to happen is, where's the question? This one. MnO4 minus 1, Mn's oxidation is +7. I mean, oxidation state is +7. Can you find the oxidation state of carbon over here? It's going to be X. Oxygen is -2. That's -2 times 2. And you got H as well. That's +1. And all of it should add up to be equal to 0. So what do you get for this? I mean, it's actually twice, but the 2 doesn't really matter in this case. X comes out to be what?
3.
So it's coming out to be +3. Mn is +2. Over here, it's carbon is +4. So we found the oxidation states of the elements, and we found out that Mn is the one that's getting reduced. So that means it gains 5 electrons, right? So it's gaining 5 electrons. It's +7 to +2. And carbon is the one that's getting oxidized. It's losing how many? Loses 1 electron. So they need to be made equal. So I need to think of a number that I'm going to multiply both with. So I can multiply this by 5 and this by 1, right? And the number of electrons lost and gained would become equal. Is that clear?
Yes.
So I need to have 5 carbons. The only thing is I would have to multiply it by 2.5, right? To have 5 carbons. So that doesn't really give me a whole number value because I need to have 5 carbons. So over here, I need to multiply this by 2.5. So I can do is I can double everything because I'm getting values in decimals. So what I can do is I can make this 10 and double this one, right? So now I can have 5 carbons, like 10 carbons in total. So this would be multiplied by 5. This would be multiplied by 10. Is that clear? And I'll have 2 Mns. 2 Mns here and 2 Mns over here as well. The only thing now that's left to do is you need to balance the oxygens and the hydrogen. So I'm going to go with the oxygens, 8 oxygens plus that's 20 oxygens plus 8, 28 oxygens. So that's 20. There should be 8 oxygens, I think, over here. So they're going to be 8 oxygens. So how many hydrogens would I have now? 16. So I already have 10 over here. So I'll have just 6 H plus 1 ions, I think. Is that clear? Is this clear? All clear? Yes or no?
Sir, how did you
Yes.
get the oxidation number for carbon for CO2H2 again?
See, carbon was unknown, so that's X. You got 2 oxygens, so that's -2 times 2, right? You've got 1 hydrogen, that's +1. And the whole thing is being multiplied by 2, I mean, it's twice, right? And the overall molecule has a charge of 0, right? So, I mean, this 2 would go away anyways. You just have to solve this. Is this clear?
Oh, all right. Yep.
So I'm just going to confirm this one if this is the 265. So is this the right equation? Where's our equation? So it's 265. That is exactly what we're getting. So the only thing that we did was we rejected the first one, 5 and 1. We rejected it because it was very hard for me to make carbons 5 because I would have to multiply it by 2.5. Is that clear?
Yes.
Now the next part is on the axis below, sketch the curve you would expect for the auto-catalyzed reaction in 1. In I, this one. I said, now you have to listen or sort of read the statement. He's saying some reactions are catalyzed by one of the products of the reaction. This is called autocatalysis. An example of autocatalysis is the reaction between magnate 7 ions and ethane dioic ions and Mn2 plus ions catalyze the reaction. The reaction is slow in the absence of a catalyst. So what happens is the reaction is going to be slow at the start. But once Mn2 plus is formed, the reaction would speed up. So what would the graph look like? The concentration would not change very fast initially. But once Mn2 plus is formed, the reaction speeds up. And then it slows down again because the reactants get used up. I mean, they kind of get used up. Is that clear?
Repeat once more.
So at this point, Mn2 plus catalysts are produced. Anyways, the thing is that he's saying it's an auto-catalyzed reaction. So right at the beginning, is the reaction going to be slow or fast? It's going to be very slow because there is no Mn2 plus produced at the very beginning. Is that clear?
Yes.
So the concentration of MnO4 minus 1 ions would change very, very slowly, or it would barely change. Okay, so there's going to be a very slow change. The gradient of the graph would be very slow. But then Mn2 plus catalyst starts getting produced and the reaction starts speeding up. Is that clear? Is this clear that the MnO4 concentration, it starts decreasing at a faster rate then? Because Mn2 plus catalyst has been formed now. So is this clear?
Yep.
And then eventually it's going to slow down because you run out of reactants. It's going to slow down. It's going and the rate would decrease again. Right. So the steepness would decrease again. Is that clear as well?
Yes.
It's just so. Describe with an aid of a pathway diagram the effect of a catalyst on a reversible reaction. Suggest why catalysts are used in industrial processes. Now he's asking for the. I mean, that's a simple O-levels question. He's just asking for the energy profile diagram, which is, I mean, the energy pathway diagram. So it's just going to be reactants and products. And after adding a catalyst, it's going to look like this. The activation energy was higher first, but after adding the catalyst, the activation energy decreases. So this is what you're going to explain. And you're going to explain that you get more effective collisions once a catalyst is added. Is this clear? So here I can show you the answer. You just have to draw this. It decreases the activation energy. And so what were the 3 marks for the diagram? And can occur at a lower temperature. Well, why did he ask for a lower temperature? I said, why catalysts are used in the industry? You had to give the importance of this. So less energy is needed. You reduce the energy requirements. The industrial process requires less energy because it now happens at a much lower temperature. So that was the 3rd mark for, I mean, this part. So is this clear? So we are on what page? Page number 10. Now try, I'm going to assign this as homework. Try and complete the rest of the paper. Hopefully today, okay? So I'm just going to assign this as a homework. ठीक है, just a second.